Let's consider that last problem we just barely finished. It was x to the third minus 7x plus 6. X to the third minus 7x plus 6. We were able to factor it. Because x minus 1 was already given. It was given to us that x minus 1 was going to be a factor. We just had to prove it. That got the whole ball rolling. If we did not know that x minus 1 was a factor, how would we have known where to start or what to do or what number to test to use synthetic division? You see where I'm going with this? Okay. The whole process only worked because the problem was nice enough to say, hey, here's one of the factors already. Here you go. And then we were able to find the remaining two. Section 3.4, that's not going to be the case. All they're going to give us is a polynomial. We have to come up with potential factors and zeros and test them using synthetic division. Okay? And you don't just choose numbers at random. This first objective is called the rational zeros theorem. This rational zeros theorem will give you a list of numbers that have the potential to be factors. You have to go through each one and test them to see if they actually are. No, it's not the quickest way. It's the way that we're going to have to do it, though. So let's talk about rational zeros theorem. First thing you need to realize this theorem only provides a list of possible, and underline the word possible, of possible rational zeros. And here's the theorem. I showed you this a few sections ago. This is just a polynomial in general form. It starts with a certain degree, and then the degrees decrease by 1 until eventually end up with a first degree term and a constant. That's all that this is saying. If the polynomial has integer coefficients, that means the coefficients in front of the variables have to be whole numbers, no fractions or decimals. Integers means whole numbers. If the polynomial has integer coefficients, then every rational zero of p of x is of the form p divided by q where p is a factor of a sub 0. That just means that's your constant. And q is a factor of a sub n. That's your leading coefficient. That's the coefficient right at the very beginning of the polynomial. A sub 0 is the last term. A sub n is the coefficient of the first term. Again, just reading a mathematical definition is hard to make sense of it. Once you see how it's used, it might make a tiny bit more sense.
But that never makes total sense.
Always makes total sense. Example 1. Use the rational zeros. Theorem. For the polynomial, I do. The rational zeros theorem is going to give us a list of possibilities, of possible rational zeros. What we first need to do is figure out values of p and values of q. Okay, so let's start with p. According to this definition, p means factors of a sub 0, or the constant right here, -8. What are factors or numbers that divide evenly into -8? 2, 1, 4, and 8. And we're forgetting, that's actually only half of them. And all are negatives, exactly. So you actually have to do this, plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. Those are all the factors representing p, or the factors of the constant. Now take a look at your leading term. The coefficient of the leading term, rather. What is the coefficient of the leading term? 1. That's pretty nice, because 1 only has 1 as its factor, or -1. So what we then do is form a list, p divided by q. This is what we end with, p divided by q. What we have to do is take each number of p and divide it separately by all the factors of q. Now luckily there's only one factor of q, so let's start one at a time. If plus or minus 1 is divided by plus or minus 1, what's the result? Plus or minus 1.
Was factors of q given to us?
No, factors of q are the factors of the leading coefficient.
And that's it?
Yep.
All right, got it.
If we take plus or minus 2 and divide it by plus or minus 1, we get plus or minus 2. If plus or minus 4 is divided by plus or minus 1, we get plus or minus 4. And plus or minus 8 divided by plus or minus 1 is plus or minus 8. Now, students often get confused and think, okay, these are all zeros. These are all of the zeros of the original polynomial, and that's false. Because how many numbers are there in this list? 8. There's 8 numbers, right? But how many zeros can there be of the polynomial? There can only be 4. Okay? This is a list of possibilities. What we're going to get to next time is how do we know which one of these actually are zeros. I don't want you to write, I just want you to watch so you can kind of be prepared. What if I chose a number at random like positive 1 and perform the synthetic division? 1, 0, -3, 3, -8. The synthetic division would look like this. What does that prove? This is not a 0 because it doesn't factor it because we got a remainder other than 0. So we would have to go through the numbers of the list to find the zeros. How many zeros are there going to be? 4. So that will be next time.